We now describe the Blayhet-Arimoto algorithm for computing the channel capacity C, which is obtained by specializing the general alternating optimization algorithm. Recall the double supremum in section 9.1, that is sup U1 in A1, sup U2 in A2, F U1 U2, where AI is a convex subset of the nth dimensional Euclidean space for I equals 1 and 2. F, a function from A1 times A2 to R, is bounded from above and is such that F is continuous and has continuous partial derivatives on A1 times A2. For all U2 in A2, there exists a unique U1 in A1 that maximizes F. And for all U1 in A1, there exists a unique U2 in A2 that maximizes F. Now we cast the computation of C into this optimization problem. Let FRQ be summation x summation y Rx times Py given x log Qx given y divided by Rx. In the above expression, R plays the role of U1 and Q plays the role of U2 in the double supremum problem. Let A1 be the set of all strictly positive input distributions R, that is, Rx is greater than 0 for all x, and summation x Rx is equal to 1, where A1 is a subset of the Euclidean space of dimension equal to the size of the alphabet x. And A2 be the set of all reverse transition matrix Q under consideration, that is, Qx given y is greater than or equal to 0 for all x and y. Qx given y is greater than 0 if and only if Py given x is greater than 0, and summation x Qx given y is equal to 1 for all y, where A2 is a subset of the Euclidean space with dimension equal to the size of the alphabet x times the size of the alphabet y. We now check that the function f, the set A1, and the set A2 so defined satisfies the requirements in the double supremum problem. First, we note that A1 and A2 are convex. Second, F is bounded from above. It is because the double summation defining F is maximized when Q is equal to Q star. In that case, the double summation is equal to the mutual information between x and y, which is upper bounded by entropy of x and further upper bounded by log of the size of the alphabet. Now in FRQ, the double summation by convention is over all x such that Rx is greater than 0 and all y such that Py given x is greater than 0. Since Qx given y is greater than 0, whenever Py given x is greater than 0, all the probabilities involved in the double summation are positive. Therefore, F is continuous and has continuous partial derivatives on A equals A1 times A2. So, we have checked all the requirements in the double supremum problem except for the requirement that F is uniquely maximized when one of the components is fixed. We will deal with that later. The double supremum now becomes sup R in A1, sup Q in A2, F of R and Q equals sup R in A1, sup Q in A2, summation x summation y, Rx times Py given x log Qx given y divided by Rx, where the supremum over all Q in A2 by lemma 9.1 is in fact a maximum equal to IRP. And by theorem 9.2, F star, which is the value of this double supremum, is in fact equal to C. We now fill in the algorithm details. By lemma 9.1, for any given R in A1, the unique Q in A2 that maximizes F is given by Qx given Y as displayed, which is the reverse transition matrix that corresponds to R as the input distribution and P as the forward transition matrix. We will show in a moment by Lagrange multipliers that for any given Q in A2, the unique input distribution R that maximizes F is given by Rx equals the product over all Y, Qx given Y, to the power Py given X, divided by a summation, which is actually the normalizing constant, because Rx is a probability distribution. In the above, the product is over all Y such that Py given X is greater than 0. Let R0 be an arbitrarily chosen, strictly positive input distribution in A1. Then Q0 in A2 can be computed according to equation 1. This forms the pair R0, Q0. Then compute R1, Q1, R2, Q2 iteratively by applying equation 2 and equation 1 alternately. It can easily be verified from equation 1 that if Rk is in A1, that is Rk is strictly positive, then Qk of x given y is greater than 0 if and only if Py given x is greater than 0. That is, Qk is in A2. Likewise, it can be verified from equation 2 that if Qk is in A2, then Rk plus 1 is strictly positive. That is, Rk plus 1 is in A1. Therefore, Rk is in A1 and Qk is in A2 for all k greater than or equal to 0. In other words, if we start with any R0 that is strictly positive, then the subsequent R's and Q's will satisfy the required constraints. It will be shown in section 9.3 that f sub k, that is f of R sub k and Q sub k, converges to f star, which is equal to C. We now discuss maximizing FRQ for a fixed Q. In this maximization problem, Qx given y, which is given, is highlighted in blue. In this maximization problem, the constraints on R are summation x Rx is equal to 1, and Rx is greater than 0 for all x. Now we use the method of Lagrange multipliers to find the best R by ignoring temporarily the positivity constraint on R in equation 2. Let J be the double summation in the maximization problem, minus lambda, the Lagrange multiplier, times summation x Rx, which is the equality constraint on the Rx's. For convenience sake, we assume that the logarithm is the natural logarithm. This makes no difference because we are doing maximization. Differentiating with respect to Rx, we have partial j by partial Rx is equal to summation y, Py given x, log Qx given y, minus log Rx minus 1 minus lambda. Upon setting partial j by partial Rx to 0, we have log of Rx is equal to summation y, Py given x, log Qx given y, minus 1 minus lambda. Or Rx is equal to e to the power minus lambda plus 1 times the product over all y, Qx given y, to the power Py given x. By considering the normalization constraint in equation 1, we see that e to the power minus lambda plus 1 is actually the normalization constant. And so we can immediately obtain Rx is equal to the product here divided by summation of the same product with x replaced by x prime over all x prime. The product in the above equation is over all y such that py given x is greater than 0, and for all such y's, qx given y is greater than 0. This implies that both the numerator and the denominator on the right-hand side are positive, and therefore Rx is greater than 0. In other words, the R thus obtained happen to satisfy the positivity constraints in equation 2, although these constraints were ignored when we set up the Lagrange multipliers. However, it is not clear that R, as given in equation 3, is a maximum or a minimum. We will show in section 9.3.2 that f is concave. Then R, as given in 3, which is unique, indeed achieves the maximum of f for a given q in A2 because R is in the interior of A1.